I like these questions because they're actual real-life examples that are useful. The second example that we're going to do after this one is an example of an actual real-life example that's not useful. So we sort of see two of them. This one I think is useful because it happens all over the place, that we're trying to find out if we've got a certain amount of material, what's the maximum volume we can make? Because if we make something bigger with the same amount of material, that's going to cost less money if you're a manufacturer, and if it costs less money, that makes more money for your company, and the company is happier. So for this one, we've got a piece of cardboard 30 centimeters long and 25 centimeters wide. Make a box with no lid. So if we draw that out and we imagine cutting out squares, just like our piece of paper example, we're going to fold them up, and that'll make a box. This will be our X, and just like before, this will be a question that we're going to solve with graphing calculator. Next year, when you take calculus, you're going to learn how to use calculus to solve these instead of using a graphing calculator. But for right now, we're going to use our graphing calculator to find these things. The first question, part A, after we've drawn it out, is to write a polynomial function to represent the volume. So our volume is length times width times height. There's our length times width times height. For part B, we need to be able to know how to graph this, or at least draw a sketch of this without our calculator, so that when we go to use our calculator in part C, we know what to look for. So now, when you're graphing this, it's already factored. So the nice thing about these volume questions is when you write it out, it's already factored. So if you wanted to find the x-intercepts, that's when the volume would be equal to 0. Here you'd get x equals 15. Here you would get x equals 12.5. So we already know that there's an x-intercept at 0, 1 at 12.5, and 1 at 15. Also, for graphing this, we need to know what kind of polynomial function this is. So for this one, we have to look at the x's, the highest power of x, and what the leading coefficient is. Is it a positive graph or is it a negative graph? So what we're going to do when we figure that out is we're just going to look at the x values. And if you multiply negative 2x times negative 2x times x, you would get 4x cubed. So if you expanded this using your skills of multiplying things out, you'd choose two of them. Maybe you chose the first two, and you would FOIL or distribute everything and get a new one. Then you would multiply all of that by x. You would get 4x cubed as your term with the highest exponent, the highest power, and leading coefficient would be 4, which is positive, which means it's an x cubed graph which acts like a line that goes up like this. So from here, we would know that our graph comes up, swoops back down, and then back up again. Now, based on the situation, the only thing that makes sense for our domain is from 0 to 12.5. You can't cut out a negative height, so nothing below 0 makes sense. You can't cut out more than 12.5, because then our smaller side, if I cut out 12.5 and 12.5, that'll use up the entire 25 centimeter side, and there would be nothing left. So again, this is the only part that we want to see. So we're going to go to our graphing calculator and type this equation in. So we've got x times 25 minus 2x times 30 minus 2x. And when we go to our window, we're going to want to see 0 to 12.5. So I'm going to go -1 to 15 just so I see a little bit more and a little bit less. For my y-axis, we don't know how high this graph goes, because if we look back at our sketch here, you'll notice that we have no indication for how high this point is right here. This is our maximum that we're interested in. But if you go to your graphing calculator and push second graph button, that'll take you to a table. And in that table, it'll tell you how big it's getting. This is better than guessing and checking, because if you guessed and checked where you start at 10, the next number you might go to 100, then you might go to 200, then 300, and then be like guessing and checking for a long time to find the maximum. The table, when we look at the values from 0 to 10 here, we can see that at 5 it's already at 1500, and that looks like it's close to its maximum. So now when I go to my window, I'm going to pick a y value that is higher than 1500. How high do you want to go? 2000, or do you want to just go to 1600? 1600. The y scale here just tells you where your ticky marks are, so I'm going to make them go by 100 so that it shows up. And sure enough, we can see the maximum now. So now to use our graphing calculator to find that maximum, we go second, calculate. Number 4 is the maximum. And we need to go to the left of it and to the right of it. So you can either use the arrow keys to go left, or you can just type in a number that you know for sure is left of it. So if I type in 3 and push enter, it'll make a little arrow. Depending on the version, my calculator draws a dotted line so you can really see what value you picked. Some of them just have the arrow. And if I go past it now to the right, because it's asking for my right bound, and I'm going to just type in 7 because that's quicker. Now my maximum is in between those two arrows. So if I push enter again, it tells me my maximum is when x is 4.52, and my y, which is my volume, is 1512,043. So you just drag your calculator screen to your paper on a test, and then you're done. So for we've done part B, which was graph. To the nearest cubic centimeter, what is the maximum volume of the box? Well, 1512 to the nearest cubic centimeter. Centimeters cubed. What size of square? Well, that was our x value. And looking down here, x is 4.52. So the nearest tenth would be 4.5 centimeters. And now our dimensions for our box will be 4.5 centimeters by, now we're going to be subtracting 9 off of each of these, so by 21 centimeters by 16 centimeters. So that would be the largest box possible to the nearest tenth of a centimeter. Just something about our graph, it's always good to label the things represented. When we graph this, this volume is what is on our y-axis. And our x-axis, our x here, is actually the height of the box. So we should write height below that graph as well. the questions you can do as a result. Questions 3 through 6, 9, and 10.